All right, the next section that we have is 16.2. This is a section all about line integrals. Essentially, this section is broken down into two distinct areas. We have our scalar line integrals, which we'll cover first, which you can see some of the theorems and definitions right here. And then later on, we have a second type of line integral, which is not a scalar line integral, but a vector line integral. All right, so we'll start with scalar line integrals. And essentially, a scalar line integral, if we look at the definition right here, a scalar line integral essentially is this quantity. That's how we're going to denote it. But when it comes to actually computing a scalar line integral, we're going to be doing something more along this line. First, essentially, what a scalar line integral has is a function. It's a scalar function f together with a curve c. And a scalar line integral is a way of combining these two in the following sense. Let's take a look at CalcPlot 3D. Where here I have a surface plotted. And we can rotate, take a look at it, sort of this like bowl shape. And then I also have the xy plane. Now imagine, just like we have in our definition here, we've got this path C, a curve C. So imagine here that what I'm going to be doing in CalcPlot is essentially, I will be talking about this, but I'm going to be doing it with a function of only two variables. So for this CalcPlot video, I'm going to be doing this. The line integral over a path C, f of x comma y, ds. So let's go back there and look. So let's first go ahead and draw a path C. The path C always lives in the domain space for whatever that function is. So since we're dealing with a function of two variables, f of x, y, which is this surface right here, our path must live in some portion of the xy plane. So let's go ahead and enable this path. So here we can see this red path that I've drawn. This path lives in the xy plane. You can look from the bottom and see it. It does live in the plane. And it lives underneath that surface. Okay, so what I want to do now is essentially imagine we take every single point on this curve, C, every single point. Let's zoom in a little bit more here. We take every single point on this surface, or excuse me, on this path C, and imagine just drawing a straight line upward to the surface. So when I say straight line, I mean directly in the z direction. So in this case, what we would have is essentially we get this curtain drawn that looks something like that. So the line integral that we just looked at tells us the area of this curtain. So let's go ahead and call this region, let's call this thing we just drew, let's call that the curtain. And then if we go back to the notes here, we'll see that this is essentially the area of that curtain. That's what this reports back. So essentially, we can think of this as, think area between xy plane and surface along a path in the xy plane. So that's what we would have for the two-dimensional example if we have f of x, y equals z. For this thing right here, you'll notice that throughout the rest of the semester, unless it really, really, really matters, we're going to be writing things down in terms of 3 dimensions. So we're going to be assuming our functions have an x, y, and z in them. Just simply because all these things, they do work in higher dimensions as well. You're not going to be asked beyond a function of 3 variables, most likely in this class. So we're going to phrase things with with three variables, but with the understanding that you can always just omit the z and do this in 2 dimensions and it still works. So essentially, that is what a scalar line integral is. It's the area along a path and a surface, where that path always is in your domain space.